Tonight, we're not looking up at the stars. We're going back, deep into Earth's own forgotten history, to a time when the air was heavy with warmth, the forests endless, and the ground trembled beneath the weight of giants. We'll wander through the age of dinosaurs, from towering plant eaters that shaped the land, to sleek, feathered hunters gliding through ancient trees, to the tiny survivors whose descendants still sing outside our windows today. If these peaceful journeys help you relax, I'd love for you to subscribe and join us again. Now, take a deep breath. Let the present fade, and together, let's walk softly into the lost world, where giants still dream beneath the stars. When I was a kid, I remember standing under the shadow of a mounted skeleton in a museum, craning my neck at that enormous skull and hearing the guide call them terrible lizards. It fit the picture they wanted us to have: hulking, scaly monsters lumbering through a lost world. But that name, coined in the 19th century when scientists were just beginning to piece together strange bones, captures only the first, clumsiest impression. The more we learned, the stranger and more familiar they became. First, they weren't lizards. Their hips and legs were built fundamentally differently. Instead of sprawling out to the sides like a crocodile's, dinosaur legs sat directly beneath the body, more like the columns under a table. That straight-legged stance let them carry more weight, run faster, and move with a kind of mechanical efficiency no reptile could match. Picture a horse's gait versus a lizard's crawl. Same planet, different design. And under those bones was another surprise: anatomy that looks eerily bird-like. Hollowed-out bones, air sacs, a furcula, the wishbone, and lung structures that point toward a system closer to modern birds than to cold-blooded reptiles. Paleontologists have found feathers, filamentous quills, and wing-like arms on species you'd never expect. Not every dinosaur had feathers, but the discovery shattered the assumption that scaly skin was universal. Some were as fluffy as a chick. Others wore sleek veins that hinted at aerodynamics. If you've ever watched a pigeon hop along a ledge, you're watching a living echo of that lineage. Warmth comes up a lot in conversations about dinosaurs, and for good reason. Many of them show evidence of elevated metabolisms. Bone microstructure tells us they grew fast, like mammals and birds, not in the slow, intermittent spurts typical of reptiles. Isotope studies and predator-prey ratios at fossil sites also suggest a higher internal temperature and energy use. Put simply, many dinosaurs didn't sunbathe to heat up. They were running their bodies from the inside out. That's one reason they could be active predators and endurance hunters, or fast-moving flockers navigating complex environments. Variation among dinosaurs is what really knocks me out. When people think dinosaur, they picture a T-Rex or a Triceratops, big, dramatic shapes. But the family tree stretches to extremes. Creatures smaller than today's sparrows, like some Paravians with delicate wing feathers barely visible to the naked eye, and titanosaurs so immense they would have reshaped landscapes as they moved, snapping soft trunks and trampling undergrowth. There were armored tanks, tiny nimble hunters, long-necked browsers that looked like living cranes, and bizarre specialists with crests and clubs for reasons we're only beginning to guess. Evolution was experimenting broadly, and every ecological niche had an answer in some dinosaur form. And here's the part I like to bring home when I watch a sparrow on my windowsill. Modern birds aren't just related to dinosaurs. They are dinosaurs. The features we use to define birds feathers, a high metabolic rate, a certain wrist structure that allows wings to fold, appear in a cascade through the dinosaur lineage. Every chirp, every migration, every flapping heart is a continuation of that story. Your backyard robin is a direct inheritor of a legacy that once included both feathered flyers and forest-crushing giants. It's a personal kind of awe, too. When I watch my dog chase a falling leaf and a mockingbird loop the same path above, I feel connected to a 160 million year experiment in body plans and behavior. The label terrible lizards served a purpose in one era, but it closes off the imagination. Once you strip away that Victorian name, you're left with a group that's dynamic, warm-blooded, inventive, and, in many ways, still very much with us. The terrible lizards, it seems, never truly vanished. Truly. Close your eyes for a moment and stretch your imagination across time. 160 million years is not just a long time. It's a different kind of time, one that moves at the pace of continents. Picture a world where land masses slowly drift like ice flows, oceans swell and withdraw, and climates change from lush, humid forests to vast, scrubby plains and back again. Through all of that shifting, dinosaurs didn't just survive, they ruled. That word ruled can sound dramatic, but it's the only word that fits. For roughly 160 million years, dinosaurs were the dominant large animals on Earth. They walked continents that were still finding their shapes. They nested in forests no human eye had ever seen, and they adapted to environments that would be unrecognizable to us. Imagine standing on a shoreline while, over millions of years, sea levels creep in and out so slowly you wouldn't notice day to day. Yet every change reshapes the places where life must find new ways to thrive. Dinosaurs lived through those slow, relentless changes. They evolved new body plans, new behaviors, new strategies for hunting and avoiding being hunted. Think of the world back then. Cycads and conifers towering like living skyscrapers, ferns carpeting the understory, and later on, the first flowering plants coloring the landscape. The air carried insects giant by today's standards. Rivers carved new paths. Mountain ranges rose. In that dynamic world, some dinosaurs grew to sizes that make our largest animals look small. Others evolved into agile, feathered hunters, no bigger than a modern turkey. There were armored tanks of muscle and bone, fleet-footed runners, and creatures that could probably outmaneuver anything we'd see in a nature documentary today. Diversity wasn't just high, it was staggering. If you've ever walked through a museum, run your fingers along the glass of a fossil display, and felt small standing next to a reconstructed spine or skull, you already have a sense of the scale. But there's another scale that hits harder when you try to place yourself in that stretch of time. Human history, your great-grandparents, the rise and fall of empires, the whole arc of written history, is a single heartbeat compared to 160 million years. Modern Homo sapiens have been around, at most, a few 100,000 years. Agriculture? That's only about 12,000 years. If the dinosaurs' reign were a full day, our entire recorded history wouldn't even fill the last minute. That perspective isn't meant to make us feel small for the sake of it. It's meant to make us feel amazed. The planet has been a stage for life for far longer than any one species' time in the spotlight. And there's a human side to this as well. When a child presses a plastic dinosaur into your hand, or traces the curve of a fossilized claw, you see a bridge between now and then, a kind of emotional tether to that deep past. Those tiny hands and wide eyes are natural responses to something big and ancient. We relate to dinosaurs because they are both familiar and utterly alien, an echo of a world that was ordered differently, but filled with the same dramas of survival, parenting, predation, and adaptation that shape life today. Adaptation is the through line of their long rule. Species that were flexible in diet or habitat could spread into new niches as continents separated or climates shifted. Some species became specialists, tuned to a narrow way of life, and others stayed generalists, ready to take advantage of whatever change came next. Evolution didn't stop for a perfect environment. It kept tinkering, experimenting, failing, and succeeding. Over millions of years, this produced not just the classic image of massive predators and long-necked giants, but delicate feathered forms, intricate social behaviors suggested by nesting grounds, and anatomical innovations that would later show up in birds. And yet, even strength has its limits. The dinosaurs' long dominance wasn't a straight path of improvement. It was a story of peaks and valleys, countless local extinctions and radiations, of ecosystems continually reshaped by forces much larger than any single species. And that's where we see something striking about life: resilience. Dinosaurs teach us that persistence is often about flexibility, about the willingness and ability to change when the world changes. As you hold that thought, it's worth letting the personal sink in. Our ancestors walked a different earth, but we carry a thread from that time. Fossils and bones tell stories that are scientific, yes, but also deeply human. Stories of curiosity, of discovery, of late-night wonder looking through a microscope, or staring up at a museum skeleton. The dinosaurs' reign may be almost impossible to imagine in full, but its remnants are threaded through our lives. In the museums we visit with our families, in the books we read as kids, in the language we use to describe power and strangeness. This is the era of giants and of the small, of dramatic environmental shifts, and of life's stubborn insistence to keep going. It's a reminder that the earth is older and more patient than we are, and that every creature's story, even ours, is a brief, beautiful stanza in a song that has been playing for a very long time. Now imagine shrinking down or stretching out until the world looks entirely different. 1 minute you're looking at a bird the size of your hand flitting through the understory. The next you're craning your neck to see a landscape dominated by a living mountain. That extraordinary range, from creatures tinier than your dinner plate to beasts longer than 3 buses parked nose to tail, is what made the Mesozoic so endlessly fascinating. Start small. Microraptor. Say the name out loud and you probably picture something adorable. A slick, jet-black animal no larger than a modern crow. But cute understates how revolutionary it was. Microraptor had feathers on its arms and legs, a long tail fan, and an iridescence that, in some specimens, looks less like plumage and more like beetle wings catching the sun. Imagine that glint as sunlight filters through a Jurassic canopy, flashes of blue and green as tiny hunters dart between ferns and conifers. These weren't awkward proto-birds struggling to fly. Many researchers now picture Microraptor as a consummate glider, launching from branch to branch, folding and spreading its limbs to steer with the precision of a parkour athlete. If you've ever watched a squirrel vault between trees, that quick, thought-like movement is a useful comparison. It's easy to picture one of these little gliders dropping onto a low branch near your head, tilting its head with a curious, almost bird-like intelligence. That tiny scale matters. When you think about ecosystems, we tend to equate dinosaurs with giants, so it's a surprise to realize how many live their lives at human scale and smaller. Pocket-sized theropods hunted insects, small lizards, and perhaps nestlings. Miniature herbivores nibbled ferns and seedlings. Many filled the same roles as modern songbirds, bats, or squirrels in their environments: pollinators, seed spreaders, pest controllers. Their small size let them exploit microhabitats, the spaces between roots, the undersides of branches, the shady grooves of ancient bark, places a Tyrannosaurus would never consider. Now tilt the lens back the other way. Argentinosaurus. The name feels like a headline because it belongs to a headline-sized creature. Stretching over 100 feet, this sauropod is an icon of gigantism. A neck snaking skyward, a barrel chest, a tail that balances like a living counterweight. To make that concrete, picture 3 city buses, end to end. Now imagine a single animal outstretching farther. When Argentinosaurus moved through a floodplain, it didn't just walk, it altered the world around it. Trees bent, water channels shifted, herds left trails in the landscape that other species followed for generations. The extremes, tiny, nimble, and gargantuan, weren't curiosities. They were solutions. Evolution experiments with form and strategy, and every body plan answered a different set of problems. Small dinosaurs survived by being quick, flexible, and often clever. They matured faster, hid better, and could exploit niches invisible to larger species. Big dinosaurs solved problems of their own, reaching food unreachable to others, processing enormous amounts of plant matter, deterring predators by sheer scale. Their bones and muscles worked like architectural masterpieces, columnar legs under weighty bodies, vertebrae structured to support necks that could swing through the canopy like cranes harvesting leaves. If you imagine their lives day to day, the differences are striking. A microraptor's day might be a blur of motion, launching at dawn, snatching insects and small vertebrates, stealing moments of warmth on sunlit branches, and hiding from nocturnal threats in the dark. A sauropod's day would be slow and rhythmic, moving deliberately from patch to patch, stripping leaves with a corkscrew sweep of its neck, chewing and digesting for hours to extract enough energy from low-quality vegetation. One is a sprinter on a micro-scale obstacle course. The other is a mobile ecosystem, reshaping plant communities just by grazing. These differences also shaped behavior and social life. Small species often relied on camouflage, speed, or flight-like abilities to survive. Some likely lived solitary lives. Others, especially those that nested in shared colonies, would have depended on group behaviors to protect young. For the giants, safety often came in numbers. Herds of sauropods may have offered protection through sheer mass, and by confusing predators with size and movement. And the lives of the young would be strikingly different. Baby sauropods were much smaller and more vulnerable than their parents, but they grew rapidly, a strategy that required enormous quantities of food and likely led to tightly coordinated family or herd dynamics. The fossil record, for all its wonder, plays tricks on our perceptions. Large bones fossilize and are easier to find, so the giants dominated early scientific imagination. It took rare, exceptionally preserved fossil beds to reveal the smaller players. Sites like Liaoning in China gave us snapshots of feathers, fur-like coverings, and delicate bones, evidence that the Mesozoic world was feathered, fuzzy, and richly textured at many scales. Once scientists started looking closer, they found that miniatures weren't anomalies. They were everywhere. That shift in perspective changed how we reconstruct ancient ecosystems. No longer were dinosaurs only monsters or lumbering titans. They were a spectrum of life, interlocking and interdependent. And there's a personal angle to all of this that makes it stick. When I picture these creatures, I think about scale as an invitation to empathy. It's easier to relate to a microraptor hopping across a branch outside your window than to a mountain-sized sauropod. But both provoke the same wonder. The tiny one shows how intricate life can be at the smallest scales. Behaviors, colors, and relationships you'd miss if you only focused on size. The giant reminds you of constraints and possibilities, what a body can do when pushed to extremes, and how ecosystems respond to presence at such magnitude. So, when you're next in a museum standing under a glass case labeled with a fossil that could fit in your hand, or staring up at vertebrae as big as barrels, let that contrast sink in. Dinosaurs didn't pick a size and stick with it. They experimented across the full spectrum, and in doing so, they taught us something vital about life. Adaptability has no single scale. The world is made up of niches, both humble and grand, and evolution will fill them all, sometimes with animals that glint like beetles and dart like thoughts, sometimes with creatures that reshape the very contours of the land. Transitioning from this idea of scale, we'll next explore how those different body sizes influenced movement and sensory perception, how being small or enormous changed the way these animals saw the world and how the world saw them. But the story of skeletons and teeth only gets us halfway there. For centuries, museum dioramas and textbooks painted dinosaurs in shades of brown and gray, the assumption being that anything bright and showy wouldn't survive fossilization. Then, paleontologists started to look more closely at the fossils themselves, and quietly, the stones began to whisper color. What's preserved in these rocks isn't paint, but something even more intimate. Microscopic organelles called melanosomes, the same pigment-bearing structures inside the feathers and skin of modern birds. Under powerful microscopes and with chemical analysis, melanosomes reveal their shapes and arrangements, and those clues can be translated into color. Long, thin melanosomes tend to indicate black or iridescent hues. Rounder, sausage-shaped ones correlate with reddish and yellow pigments. In some fossils, we even find layers of tiny structures arranged in ways that scatter light and produce metallic sheens. Structural colors, very much like the iridescence of a hummingbird or a starling's glossy head. If you picture this with me, it's almost startling. Imagine walking into a Jurassic forest and sunlight slices through the canopy. On a branch, a small predator flicks its wings. Instead of drab patches of brown, you see a flash of deep blue which, depending on the angle, turns to green. Along the ground, a tail banded in rusty reds flicks as the animal darts, an honest signal to rivals, or a clever blur that confuses predators. The fossil record gives us snapshots of that spectacle. Some species once thought monochrome are now reconstructed with elegant counter-shading, darker on top, lighter underneath. The same trick many modern animals use to disappear from predators' sightlines. It helps to think about birds you know. The pigeon on your stoop isn't dull at all up close. There are iridescent greens and purples around its neck, produced by microstructures in the feathers. The peacock's fan is a textbook example of structural color. Dinosaurs, as it turns out, had access to the same optical toolkit. In certain feathered fossils, we find melanosomes packed in precise arrays, nanoscopic architecture that would have created shimmering, angle-dependent colors. When those structures are preserved, they tell a clear story. Nature had already invented some of the most spectacular tricks of plumage long before humans appeared. Color also appears in patterns, and patterns tell stories about behavior. One famous fossil shows a small dinosaur coated in ginger and white banding along its tail, what a modern biologist would call disruptive patterning. It's not hard to relate to these patterns because we see the same strategies every day. Camo clothing breaks up outlines. Racing stripes direct attention. Team colors announce identity. In dinosaurs, bright patches could have signaled health and fitness during courtship, intimidated rivals, or guided young animals through dense forest. Color was a social language as much as a survival tool. There's an emotional dimension to this rediscovery too. For most of us, a grayscale dinosaur is easier to fit into the world of extinction, stoic bones in a dusty past. But when you realize these animals flashed brilliant blues, glowed with coppery reds, or shimmered with golden highlights, they feel closer, more immediate. They were not simply distant, alien monsters. They were actors with style, with daily rituals and visual drama. It's like discovering that an old family album has colorized photographs. Suddenly those moments feel more alive, more intimate. Science hasn't just given us a palette. It's shown how different kinds of color are made. Pigment-based colors come from chemical compounds, melanins that absorb certain wavelengths of light. Structural colors don't depend on pigment. They arise from the physical arrangement of matter at the nanoscale, bending and reflecting light to create iridescence and metallic lusters. Think of the difference between dyeing cloth and weaving a shiny brocade. Both produce color, but the mechanisms and the effects are distinct. Many dinosaurs probably used both, layering pigment and structure to achieve intense, changing displays, and skin wasn't left out. While feathers preserve more readily, there are specimens preserving scaly skin with evidence of pigment. That suggests that even the larger, non-feathered dinosaurs might have had patterns and hues we're only beginning to imagine. Picture a large herbivore with subtle counter-shading and a flash of contrasting color across the flanks, used to communicate during mating season or to warn of parasites. It's tempting to imagine herd dynamics shaped as much by visual signals as by smell and sound. The implications ripple into how we reconstruct behavior. Bright, conspicuous colors imply a world with visual communication, courtship dances, status displays, species recognition, maybe even parental signaling. Camouflage patterns imply complex predator-prey games played under filtered light. Structural iridescence suggests that movement itself could create shifting shows of color, turning a simple wing beat into an attention-grabbing performance. For scientists, each fossilized melanosome is a tiny message from a lost animal about how it lived, moved, and interacted. On a human level, this changes our relationship to dinosaurs. When a child today sees a reconstruction with brilliant plumage, they don't meet a flat, lifeless statue. They meet a creature with character. That matters. It refines our empathy and expands how we imagine prehistoric ecosystems. It also reminds us of continuity. The visual tricks and social dances we admire in birds evolved far earlier than we thought. The feathered dinosaur on a museum wall is not merely an ancestor of birds. It's a participant in the same evolutionary theater. So the next time you picture a Mesozoic landscape, try to drop the grayscale filter. See sunlight slanting through cycads and ginkgos, catching on feathers that gleam like oil on water, lighting up scales with coppery flashes. Hear the subtle rustle as color becomes motion, and remember that what we once thought was dull was, in truth, a living mosaic, a world stitched in light and pigment, full of color-driven lives. Those shimmering palettes don't just change what dinosaurs looked like, they change how we understand what those animals meant to each other and to their environments. So what changed everything? Feathers. Not as a late tweak for flight, but as a multi-tool evolution that rewrote how dinosaurs lived, fought, mated, and even grieved. Picture this with me. The Jurassic and Cretaceous landscapes, not as a drab parade of gray, scaly hulks, but as stages filled with texture, pattern, and motion. Feathers catching the light, flaring in combat, puffing up against a cold wind. That image isn't fancy reconstruction, it's what the fossil record has been quietly telling us for decades. Let's start with warmth. We tend to think of feathers and flight together, but the earliest feathers were often simple filaments, downy, insulating, more like a modern chick's first fuzz than a swan's wing. For small dinosaurs living in cooler climates or alternating temperatures, a coat of down would have been a lifesaver. Thermoregulation matters. If you've ever pulled an extra sweater over your shoulders on a chilly morning, you have an intuitive grasp of why a bit of fluff could mean the difference between thriving and freezing. For baby dinosaurs, too, that fuzz was a literal life jacket. Paleontologists find evidence that some larger theropods, like tyrannosaurs, may have hatched with soft down. The thought of a tiny, fuzzy tyrannosaur chick, awkward, bright-eyed, and insulated from the cold, collides with our old Hollywood images and humanizes these animals in a surprising way. But feathers were also showy. Think of a peacock, but older. Paleontologists can now read color from fossilized feathers by studying microscopic structures called melanosomes. That's how we know some non-avian dinosaurs sported blacks, whites, russets, and even iridescent sheens. Anchiornis, a crow-sized dinosaur, likely had a black and white body with a reddish crest. The kind of pattern that says, "Look at me," across a million years. Microraptors' glossy, iridescent feathers suggest light-bending color, maybe used to signal mates or intimidate rivals. When you picture these animals, imagine not just stealth and toothy jaws, but plumage flashing in mating dances, bright crests bobbing as two males size each other up. It's a scene that feels intimate because it's familiar. Every bit of animal courtship you've seen at the bird feeder, only older and stranger. And then there's movement. Feathers changed how dinosaurs moved through their world. Long wing-like feathers on arms and legs appear in several lineages long before true powered flight evolved. Some small theropods use these feathered limbs for balance while running, or to create drag during leaps, or even to help scramble up inclines, what scientists now call wing-assisted incline running. Microraptor might have used its four-winged body to glide between trees, so feathers at first were more aerodynamic tuning knobs than fully developed wings. This is elegantly practical evolution, structures repurposed over time for new uses. We also have to rethink the look of predators we've mythologized. Raptors, Velociraptor and its kin, are still terrifying, but not scaly velociraptors stalking like reptiles from an old movie. Fossils show quill knobs on forearms, attachment points for feathers. Imagine Velociraptor with a mantle of sleek plumage, flaring during a display or folding neatly while stalking. That transforms how we interpret their behavior. Feathered wings could have been used for brooding, shielding young, or flash displays to confuse prey. And large tyrannosaurs. Discoveries like Eutyrannus, a feathered tyrannosaurid, forced a wholesale reassessment. It was literally covered in a coat of filamentous feathers, proof that even big predators wore plumage, at least at certain life stages or in certain climates. The idea that T-Rex lumbered about as a naked, scale-clad colossus is giving way to images of animals with patches of fuzz, plumage accents, and complex skin coverings. Beyond utility, feathers added a social and ecological layer. Color and pattern communicate. They advertise fitness, delineate species, confuse predators, and warn rivals. In a world where survival is a constant negotiation, being able to signal, "I'm strong," or "hands off" at a glance is a powerful advantage. Imagine being a small herbivore and seeing a flash of bright color on a predator. Does that mean danger, courtship, or bluff? That ambiguity would shape daily decisions and evolutionary paths. There's a human connection here worth pausing on. Our fascination with feathers is ancient. We've worn them, decorated with them, used them as symbols. When scientists tell us dinosaurs had feathers, it shrinks the distance between us and these creatures. It's easier to empathize with a fluffy hatchling, or to picture a courtship dance when the participants have crests and plumes rather than only scales. We see components of ourselves, care for offspring, competition for mates, the desire to be noticed in these feathered behaviors. That's why these discoveries land emotionally. They're not just anatomical footnotes, they're stories about living animals. Finally, consider the broader stage. Feathers turned the prehistoric world into a theater. Movement and color layered atop teeth and claws meant that selection worked on display as much as it did on raw strength. Beauty and survival were not mutually exclusive. They were often the same wing. A raptor could be a fearsome hunter and a flamboyant performer. A tyrannosaur might have used fuzz to keep warm and to charm a mate. That overlap, function and flair intertwined, reframes the way we imagine the Mesozoic. So the feathered revelation isn't a minor costume change for dinosaurs. It's a paradigm shift that affects physiology, behavior, ecology, and our emotional connection to these animals. Next, we'll trace how researchers unravel those colors and patterns from fossilized filaments and what those hues tell us about daily life in a world where the sky and underbrush were streaked with feathered motion. But that was only part of the story. For decades, museums and textbooks painted dinosaurs as giant, sluggish reptiles, cold-blooded behemoths basking in the sun like modern lizards, waiting for prey to blunder by. Today, the evidence forces us to rewrite that image. These creatures weren't slow-moving stones. They were warm-blooded giants, more like living furnaces than cold rocks. And once you imagine them that way, everything about their lives clicks into place. Start with the bones. Paleontologists don't just dig up fossils, they read them like tree rings. Inside dinosaur bones, you can see growth rings, patterns that tell a story of rapid growth and high metabolism. Young dinosaurs added bone fast, year after year, in bursts that look a lot more like mammals and birds than like turtles. That kind of growth needs fuel, lots of it. It means their bodies burned energy at a steady, brisk pace, not only when they were active, but day in and day out. Then there are the oxygen traces locked in fossil teeth and bones. Tiny variations in oxygen isotopes act like biochemical thermometers. When scientists measure those ratios, they find values consistent with relatively stable and high body temperatures. In other words, many dinosaurs maintained a warm internal environment, independent of the outside air, a hallmark of what we call endothermy, or warm-bloodedness. That small, invisible chemical signature flips the old script. These animals generated and regulated their own heat. Think about what that would actually feel like. Imagine walking with a herd of hadrosaurs beneath a twilight canopy at high latitudes, where winter nights can be bitter. Because they could produce their own heat, these dinosaurs could tolerate climates that would freeze a modern reptile's blood. They could live and feed in polar forests, take advantage of extended daylight in summer, and cope with the lean times of winter in ways cold-blooded animals simply can't. Warmth gave them flexibility. Warm-bloodedness also opens the door to endurance. It's one thing to sprint. It's another to travel dozens or hundreds of kilometers, following seasonal food sources. Evidence from trackways and bone chemistry suggests some species undertook long migrations, crossing landscapes in coordinated waves. Picture the scene. Long-necked sauropods slowly moving across a changing plain, muscle and lung working in steady sync, driven not by sun-warmed sluggishness, but by internal, sustained energy. That endurance is a kind of freedom, the ability to explore, to follow resources, to adapt. And then there's the human part of the story, care and social complexity, raising young the way many dinosaurs did, protecting nests, feeding juveniles, keeping them warm and supervised, takes constant energy and attention. Cold-blooded parents can't easily sustain that kind of investment. But warm-blooded bodies can support prolonged care, brooding, guarding, even feeding. Fossils showing nests, brooding postures, and growth profiles of juveniles point to family behaviors we can empathize with. When we see a mother dinosaur shading her hatchlings or shepherding them to safety, it's easier to relate, because it mirrors the care many of us know from our own lives. All of this changes how we imagine dinosaur behavior. No longer are they motionless statues waiting for fate. They are active, persistent, and present in their environments. They foraged at dawn and dusk, migrated with the seasons, defended young with a ferocity born of protective instinct and the metabolic power to sustain it. They were warm, alive, and in constant motion, not just surviving, but thriving. So next time you picture a dinosaur, try to feel the heat. Think of the panting breath after a chase, the steady thrum of a heart powering miles of migration, the soft care of a parent with energy to spare. These were not relics of a sluggish past. They were dynamic animals, their internal fires burning bright in a world far different from our own, but in many ways, closer to us than we once believed. Not every dinosaur story is about teeth and claws. Some of the clearest messages that came down to us in stone are about care. Imagine a low mound of packed earth, the surface broken open to reveal an array of eggs arranged in neat circles. Lying across the top is the outline of a bird-like body, wings folded protectively over the clutch, feathers splayed like a blanket. That scene isn't a guess. It's the fossil of a parent literally caught in the act of brooding. Oviraptorids, such as Citipati, were found in exactly that pose in Mongolia. A circle of eggs with a grown dinosaur crouched over them, wings and tail wrapped around the nest. At first, scientists called these animals egg thieves because they were found on nests. Now we read them differently, as guardians. Then there is Egg Mountain in Montana, where paleontologists found whole nesting colonies of Maiasaura, the good mother lizard. There, nests sit in clusters, and inside them were not just embryos, but remains of juveniles still small enough to fit in a burrow. The bones show fast growth, but also signs that the young couldn't have fed themselves immediately on tough plant material. The most convincing interpretation? Parents were returning to feed, warm, and protect their young. The word good in their nickname comes from a real pattern of parental investment written into the rock. We also find evidence in the tiniest things: eggshell fragments, the spacing of nests, and the layers of sediment that tell us when incubation happened. Some eggs are found tucked beneath feather impressions. Others are piled in careful circles that suggest repeated use of the same site. Bone histology, the microscopic study of growth rings in dinosaur bones, reveals rapid growth rates in juveniles that match the kind of provisioning seen in animals today that are fed by parents. These are all clues that parenting was a strategy, not an afterthought. And then there are the footprints. Trackways across ancient mudflats sometimes preserve adults and juveniles walking together. Small prints pressed reverently beside larger ones, like a family strolling. In a few places, the tracks are so close that you can almost hear the imagined hush. Adults between youngsters in danger. A line of tiny feet shadowed by long strides. Those fossilized walks tell us about daily life. Migration, foraging, learning to move as a unit. They show movement and proximity, the physical expression of care, staying together. What makes these scenes so affecting is how easily we can see ourselves in them. Think about the little rituals in your own family. Bending to tie a shoelace, spreading a blanket over a sleeping child, the way someone will stand guard when a baby finally falls asleep. Those same practical gestures are preserved in dinosaur behavior. A wing spread to shelter eggs from a sudden cold snap, a parent circling while the others feed, juveniles clustering for warmth. Love here looks the same as it often looks for survival. Attention, patience, the willingness to risk for someone smaller. We don't have sentiment in the fossil record in the way a diary records a parent's worry, but we do have the architecture of care. Nesting colonies, brooding postures, juveniles in need of feeding and protection, trackways showing company. All of these are practical solutions to the problem of raising the next generation. And because these behaviors increase the odds of offspring surviving, they were written into the very patterns of dinosaur life. So when you picture that crouched body over a circle of eggs, or the little prints beside a long stride, think of the continuity. The tenderness frozen in stone is not a distant curiosity. It is a kind of kinship. Our impulse to protect, to teach, to stay close in the face of danger. Those are old strategies. Love, in its practical, everyday forms, helped species cross the millennia. The fossils don't just show how dinosaurs fought and ate. They show how they loved in the only way that matters for survival, by caring enough to give life a chance. Picture yourself on a sun-baked plain, wind moving the tall ferns, and then, not a roar like in the movies, but a long, low note rolling over the landscape, something you feel in your chest before your ears catch up. That's the kind of soundscape we're talking about. Not silence, but a chorus shaped by bone and air. Some dinosaurs literally had built-in instruments. In species like Parasaurolophus, evolution carved out hollow crests and convoluted nasal chambers that acted like resonating tubes. Imagine a hollow horn, curved and looped atop the skull. When air passed through, those chambers could amplify certain frequencies, stretching a single exhale into a haunting, trumpet-like call. Paleontologists have CT scanned those crests and even built physical models and computer simulations to see what they might have sounded like. The results aren't just guesses. They point to deep, resonant tones with rich harmonics, the kind of sound that travels for miles across open plains. And it wasn't only about being loud. Some dinosaurs likely communicated with infrasound, pitches below what our ears can pick up. Think of the sensation of a distant thunderhead, or the bass at a concert that makes your chest vibrate. Infrasound behaves similarly, slipping under the noise of wind and foliage and carrying over long distances. Elephants use it to coordinate across kilometers. There's growing evidence some sauropods or other large species might have done the same. So you wouldn't always hear a message from a dinosaur. Sometimes you'd feel it, a subtle earth hum signal that said, "Gather, danger," or "Stay close." These vocal capabilities weren't just anatomical flukes. They fit into daily life. A resonant call could announce mating readiness, keep a dispersed herd together, or warn of predators without revealing an exact location. The structure of inner ears in several fossil species suggests they were tuned to lower frequencies, reinforcing the idea that dinosaurs were listening for low notes as much as they were producing them. To make this personal, next time you're in a wide, open place and the wind carries a distant, deep sound, picture a Parasaurolophus answering across the grasses. Imagine the vibration settling in your ribs. Not frightening, but uncanny, a reminder that the world has always been filled with signals we don't immediately recognize. The age of dinosaurs wasn't only a visual spectacle of armor and teeth. It was an aural environment shaped by bone, air, and intention. Their songs were written into the landscape itself, a soundtrack of crests and chambers that turned the earth into a giant living instrument. In the next segment, we'll explore how those songs intersected with movement and behavior, how sound, sight, and social life braided together to create the full, lived experience of these ancient creatures. And then there were the ones you can't help but stop for, the sauropods. Not just big, but engineered on a scale that seems almost impossible when you first try to picture it. Think of buildings that walk, towers of muscle and bone, balanced on gigantic pillar-like legs, with necks that reached out across the landscape like living cranes. Their anatomy reads like a solutions manual for the problems that come with being enormous. Start with the neck. Some sauropods had necks longer than a city bus. some species pushed toward truly jaw-dropping lengths. That raises a mechanical puzzle. How do you get blood all the way to a head hanging tens of feet above the heart? Paleontologists and engineers have wrestled with this question for decades. The simplest answer is that sauropods evolved cardiovascular systems up to the task, hearts and vessels scaled in ways that would make modern hearts seem tiny in comparison. Imagine a heart large enough to push blood up those extended necks with barely a pause. It's a useful mental image. Not a single monstrous organ, but a cardiovascular system tuned for extreme heights. A steady pump that kept a 20, 40, even 70-ton body alive and active. But skeletons that massive shouldn't be bone after bone of raw, heavy rock. Sauropods solved that too. Their bones were riddled with internal air spaces, pneumatic cavities that lightened the load without sacrificing strength. It's the same trick engineers use when building bridges and aircraft today. Material where it counts, hollow where it doesn't. CT scans of fossil bones reveal a maze of internal struts and chambers. Those air pockets made sauropod bones both strong and astonishingly efficient, allowing a frame that could support the weight of dozens of African elephants stacked together while remaining mobile. Standing beneath one, or at least standing beneath a life-sized reconstruction or cast, is where the facts turn into feeling. Imagine stepping out from bright sunlight into a sudden shadow that blots the whole world for a second. The air cools a degree or two. The light slants differently. Your first reflex is to look up, and there it is. A limb as thick as a telephone pole, a belly arching like the hull of a ship, a neck that keeps going until your eyes want to stop but can't. The ground under your feet shivers in a way that modern animals don't usually produce, a soft, rolling tremor that reverberates up through shoes and bones. It's not violent, not the violent rumble of an earthquake, but a deep, steady pulse, the memory of a rhythm that once shaped the land itself. That tremor had consequences. Trackways preserved in rock show groups of sauropods moving across floodplains and coastal plains in relatively straight lines, leaving prints that stretch for miles. The pressure of their steps compacted soils, creating paths and water channels. Vegetation patterns would have been different in corridors traversed by giants. Animals and plants adapted to those rhythms. Low plants that could take the stomp, birds and small mammals that exploited the disturbed ground. In short, sauropods didn't just live on the landscape, they engineered it. They also likely communicated in ways that used their size. Low-frequency sounds, the kind of infrasound modern elephants use to talk over long distances, could have traveled for kilometers through the ground and air. Standing near a sauropod might have been a multi-sensory experience. The subsonic thrum underfoot, the faint vibration in your jawbones, perhaps even a low humming in the air as breath passed through enormous lungs and air sacs. The entire scene would feel ancient in the deepest way. The environment responding to beings that exist on a scale our daily lives never approach. Because these animals were so large, modern researchers have had to invent new ways of studying them. Biomechanical modeling uses computer simulations to test how a 70-ton body could move without buckling. Bone histology, looking at microscopic structure, tells us how fast they grew. Some sauropods raced through life, reaching full size in a few decades, a growth pattern that required prodigious metabolism and intake of food. Fossilized trackways and nesting sites give clues to social behavior. Some species moved in groups. Others left nesting colonies, hinting at parental strategies and communal living. Put together, the bones, the tracks, and the models create a picture of animals that were not only mechanically brilliant, but ecologically central. And yet, for all that engineering, there's something almost tender in the image of these giants. Picture a long-necked mother reaching down to nudge a youngster, the tail sweeping like a counterweight as the calf learns to take its first heavy steps. Or imagine a herd of adults moving at dawn, their silhouettes cutting through mist, the sound of their passage a low, slow percussion. Those are scenes people can relate to, because at the heart of it, these were families, populations, lives lived day by day. The scale may be beyond our direct experience, but the social rhythms aren't alien. Feeding, moving, protecting young, responding to droughts and floods, making do in a changing world. That makes them doubly fascinating. When you read about a 70-ton sauropod, it's easy to treat the number as abstract. But when you add heart and breath and family and footprints that changed rivers, those numbers become lived reality. Suddenly, you're not just reading about bones. You're imagining a being whose existence altered the landscape, whose very steps regulated the ecology around it. And because they were built with such clever anatomical tricks, pneumatic bones, massive hearts, columnar limbs, they became more than a sum of parts. They were biological solutions to the problem of being enormous, elegant, and pragmatic. So the next time you picture a dinosaur, don't default to teeth and claws. Picture a titan that shook the ground, the air around it humming with life. Picture engineering so refined it could carry a city's worth of weight across a plain without collapsing under its own bulk. Those were the sauropods, miracles of structure and scale, living proof that life can find ingenious ways to inhabit even the most extreme niches. You can almost feel the moment, the air hanging heavy, the low rustle of leaves, a shadow that doesn't move until the last possible second. That pause before action is where precision lives. It's where muscle and brain meet, and where the hunters we think of as pure brute force reveal themselves as calculating artists of survival. Take Tyrannosaurus rex. The popular image is a walking wrecking ball, and there's truth to that. T-Rex had a bite force greater than any land animal in history. When those jaws closed, they didn't just tear flesh, they pulverized bone, crushed tendons, and exposed marrow like a locked safe forced open. But that raw power wasn't random. It was a final move in a chain of choices honed by millions of years of evolution. Think about when you've had to do something important. You don't fling yourself at it blindly. You read the room. You wait for the right line. You pick the easiest angle. A T-Rex did the same, on a life or death scale. Fossils show wear patterns, healed bones, and bite marks that tell a story. Ambushes after patient stalks, stumbles exploited rather than rushing a healthy herd, and kills chosen for the highest payoff with the least risk. This was a predator that could afford to be selective, with the kind of force that could crush bone, making sure the prey was in the right position before delivering the lethal bite was smart survival, not wasteful bravado. Sense played a big part in that intelligence. T-Rex likely had excellent eyesight. Forward-facing eyes hint at good depth perception. the kind of vision that helps a hunter judge distance and timing. And its olfactory bulbs were large, suggesting an acute sense of smell for tracking or detecting carcasses from a distance. So the picture you should hold in your head isn't a mindless marauder. It's a patient giant that combined sensory acuity with devastating mechanics. It waited, assessed, and then applied power with surgical effect. If T-Rex is the heavy hitter, Velociraptor is the scalpel. Far from the movie monsters we grew up with, the real Velociraptor was small, closer to the size of a large dog or a turkey than a person, and feathered. That silhouette changes everything. Feathers weren't just for show, they were part of a finely tuned system for balance, maneuverability, and signaling. Imagine a lithe hunter weaving through underbrush, using feathers to stabilize rapid turns, to leap, and to maintain balance while grappling with prey. And then there are the claws. The famous sickle-shaped petal claw of Velociraptor was sharper than a kitchen knife and designed to do very specific work. Instead of relying on overwhelming force, Velociraptors used precision slashes and controlled gripping. Their hands could grasp, their necks were flexible, and their brains, relative to body size, were bigger than many other dinosaurs. This combination created a predator that blended power with finesse. It could time a strike perfectly, aim for vulnerable spots, and use momentum to its advantage. If you've ever watched a skilled chef, you've seen the same principle: deliberate, economical motions that achieve maximum effect. You don't hack at an onion, you slice cleanly. That's how these dinosaurs operated. Evolution didn't simply stack muscle on muscle, it distributed tools across the body: teeth built for crushing, claws for slashing, senses optimized for detection, each one refined for a purpose. There's elegance in that balance. Precision isn't just small movements. It's the wisdom to choose when to use force and when to conserve it. A T-Rex that bit recklessly risked wasting energy and damaging its own teeth. A Velociraptor that lunged without calculating trajectory could lose its meal, or worse, injure itself. Natural selection favored individuals that combined patience with action, instinct with calculation. Over generations, that made them better hunters, not necessarily bigger or meaner, but smarter in a focused way. We can relate to that. Whether you're a parent deciding the right moment to correct a child, an athlete timing a sprint, or someone sending an important email after rereading it twice, you know the value of waiting for the right instant. There's a predator's logic in those choices: assess, align, execute. It's deceptively simple and brutally effective. The fossil record gives us small, telling details. Bite marks on bones suggest that T-Rex sometimes targeted joints or neck regions to incapacitate prey quickly. Again, an economy of effort. Trackways and limb bones of raptors show adaptations for quick directional changes, hinting at ambush tactics and agile pursuits. Feather impressions and quill knobs, preserved in some raptor fossils, remind us these animals were not about raw force alone. They were systems, bioengineered for a lifestyle of calculated aggression. There's also a social dimension. Some studies suggest group behaviors in dromaeosaurs, meaning these predators could coordinate. Imagine a duo or trio working a flank, driving an animal toward a member ready to strike. Coordinated hunting requires signals, timing, and shared understanding. Another layer of precision, written not in a single tooth or claw, but in behaviors passed down and refined through generations. And precision isn't only physical. Timing your attack to appraise tiredness, choosing a sick individual over a healthy one, or stalking from cover until the herd's guard is down. Those are mental strategies. Paleontologists tease these ideas out from subtle clues, healed injuries that imply escape from failed attacks, bite marks on healed bones indicating scavenging or repeated confrontations, and the distribution of fossils suggesting preferred hunting grounds. Each clue adds up to a picture of hunters who thought, on instinctual, evolutionary timescales, and acted with purpose. So when you picture predators like T-Rex and Velociraptor, try to see their economy of motion and decision. Let go of the idea that strength and precision are opposites. Evolution doesn't favor extremes so much as efficiency. A crushing bite is precise when it's delivered to the right place at the right time. A slicing claw is powerful when it's aimed at a weakness. Power and patience, instinct and intellect. These are not separate traits, but complements, every bit as relevant to a modern surgeon's scalpel as to a Mesozoic hunter's tooth. In the end, the fossilized tooth marks and feathered arms are more than paleontological curiosities. They're echoes of a timeless lesson. Precision is a form of strength, whether across millions of years or in your next decisive moment. The most formidable predators aren't the loudest or the largest. They're the ones who understand when to hold back and when to strike. Their legacy is written in claw and tooth, and in the quiet, exacting patience that turned survival into mastery. Then came the flash. 66 million years ago, a rock from space struck Earth with a fury greater than billions of bombs. The air burned, the oceans rose, and the sun disappeared behind clouds of ash. In weeks, the world grew cold. Forests died, seas changed color, and silence spread across continents. The age of dinosaurs ended not with a whimper, but with the roar of the heavens. Imagine it not as a headline in a textbook, but as a single day that broke everything everyone had ever known. Picture standing on the edge of a shallow sea, the kind you might visit on vacation, and seeing a second sun appear on the horizon, brighter than anything you've ever seen. That flash would have been so intense it vaporized everything nearby. Rocks and water turned instantly to superheated gas. The ground would have shaken with an incomprehensible force, a shock wave that traveled faster than any sound you know. If you've ever stood next to a thunderclap that made your chest vibrate, multiply that by 1,000,000, and you begin to get a sense of the scale. Then came the rain, not gentle drops, but molten spherules and incandescent ash raining back down from the sky. Those hot particles set forests ablaze thousands of miles from the impact site. Within days, firestorms consumed huge swaths of plant life, and the skies filled with so much smoke and soot that the sun was blotted out. Without sunlight, plants stopped photosynthesizing. Think about how quickly a garden wilts when it is kept in darkness for a week. Now imagine that across whole continents for months. The base of every food chain began to collapse. It's tempting to imagine the dinosaurs as monstrous, invulnerable creatures, titans immune to the whims of fate. But they were animals like us, dependent on food, water, and a climate they were adapted to. When the light failed and plants withered, the herbivores starved first. Carnivores followed not because the sky was dramatic, but because there was simply nothing left to eat. The great roaming herds, the apex predators, the creatures that dominated for tens of millions of years, all of them faced the same brutal arithmetic. Survival requires energy, and the energy lines were cut. The oceans didn't escape. The impact threw huge amounts of debris and sulfate aerosols into the atmosphere, and when that material spread, it changed the chemistry of rain. Acid rain would have scoured both plant and plankton alike. Plankton are tiny, but they are the foundation of marine food webs. When they died or went dormant, shells began to dissolve and food chains collapsed from the bottom up. Coastal ecosystems were shredded by megatsunamis generated by the impact, walls of water that inundated continental shelves and wiped out shallow marine life in a single, catastrophic sweep. Time after the first week becomes a bleak blur. The initial heat gave way to a dark, cold, impact winter. Temperatures plummeted as sunlight was blocked by dust and soot, in some places staying low for years. Winters became long and punishing. In a world adapted to a particular rhythm of seasons, this sudden change was devastating. The silence that followed the roar wasn't just the sound of empty forests. It was the near-total collapse of the ecosystems that had supported those sounds for millions of years. But within that ash and desolation, survival stories flicker like embers. Not every species died. Small, adaptable creatures, especially those that could burrow, hide in fresh water, eat a broad diet, or enter long periods of dormancy, had a much better chance. Think of a mouse slipping into a burrow, living on stored seeds, hunkering down through a long winter. That kind of lifestyle gave early mammals, and some bird-like dinosaurs, a narrow window to persist. In the oceans, some small, cold-tolerant organisms survived in refuges. Life clung on in pockets and places where conditions were less extreme. There's a humbling human lesson here. We like to imagine ourselves far above other creatures, insulated by technology and knowledge. But a single random event from space altered the trajectory of life on Earth. It's a reminder that our long-term security rests on fragile systems, atmosphere, climate, biodiversity, that can be tipped in a single strike. It's also a reminder of resilience. From the ruins of the Cretaceous came opportunities. With dominant groups gone, ecological niches opened. Mammals diversified. Some grew larger. Others explored new diets and habitats. What had been constraints were suddenly possibilities. When you visualize the fall of the giants, try to make it a sensory memory, not just an abstract fact. Picture ash settling on the leaves of a plant you know. Imagine the sudden drop in temperature so sharp you pull your jacket tighter, though summer should be warm. Or feel the eeriness of walking through a forest where no birdsong returns. Those images make the past intimate, and they help translate enormous time into something our minds can grasp. Scientists have reconstructed this story from clues. A global layer of iridium-rich dust, shocked minerals, and a massive crater off the Yucatan Peninsula, the Chicxulub crater. Together, those clues form a mosaic. Each fossil bed where creatures abruptly disappear, each chemical anomaly in ancient sediments feeds into the same narrative, a sudden, planet-scale disturbance. And yet, even as we stand in awe of that cataclysm, there's a quieter, ongoing drama. Extinction is not only dramatic massacres, it's also small, slow, invisible losses, as environments shift and species fail to adapt. The asteroid taught us both. Catastrophe can strike, but continual incremental pressures can be just as deadly over time. So when you look at a living bird, a sparrow on a windowsill, a crow on a telephone wire, know that you're seeing a descendant of survivors. The world those birds inhabit is a direct consequence of that terrible day. The scent of pine that remains after fires, the soil enriched by ash, the ecological vacancies filled by mammals, birds, insects, and plants that found ways to endure. The fall of the giants is not only the story of an ending, it's also the beginning of the world we live in, shaped by loss and by the stubborn persistence of life. Yet not all perished. One branch of small feathered dinosaurs didn't just cling to life on the ground. They took to the skies. We call them birds. Imagine a robin on a rainy morning, shaking beads of water from its wings. Think of a penguin carving a path through Antarctic ice, or a sparrow hopping along a city sidewalk, unbothered by the rush around it. Those familiar everyday creatures are the direct, living descendants of the dinosaurs we've been tracking through time. When you see a robin flick its head or hear a sparrow's sharp chirp, you are listening to an echo of the Mesozoic. Those feathers are more than pretty plumage. They're a living memory of a world when giants stomped the earth. To make this feel personal, picture the first time you watched a bird take off. Maybe it was a sudden burst, wings beating, the body lifting, the tail fanning to steer. There's something quietly miraculous about that moment. For me, it's the flash of understanding. A fragile animal, smaller than my hand, negotiating air in a way that connects it to creatures that lived alongside Tyrannosaurus and Triceratops. That connection is the through line of survival. While most lineages vanished, this one adapted. How did they do it? Size and feathers were part of the answer. Many of the dinosaurs closest to birds were small, agile theropods, creatures built for speed and dexterity. Feathers, which originally evolved for insulation or display, eventually became the tools of flight. Over generations, bones lightened, forelimbs lengthened, and muscles and respiratory systems changed so these animals could lift off. Flight itself opened up new ways to find food, escape predators, and colonize environments unreachable to larger, land-bound animals. When the asteroid hit, size worked against the giants. Being small, mobile, and adaptable gave these feathered survivors an edge. But don't think all birds are the same. Evolution takes its own winding paths. Some lineages spread their wings across every habitat on Earth. Others, in a twist of evolutionary irony, gave up powered flight entirely and took to the water or the ground. Penguins, for example, are birds that became superb swimmers. Their wings transformed into flippers, their bodies tuned for cutting through cold seas. Ostriches and emus traded aerial freedom for speed on land. Even within cities, pigeons and starlings found niches where they thrive among people. The diversity you see at a feeder or a park bench is the result of 66 million years of trial, error, and adaptation. That long survival is written into their bodies. Look at a bird's skeleton, and you'll see relics of dinosaur design, a fused wishbone that helps brace the chest for wing beats, hollow bones that keep weight down, and a wrist structure adapted for flapping and folding. Fossils discovered in the last few decades, like Archaeopteryx and a parade of feathered dinosaurs from China, fill the gaps in our story, showing transitional forms where feathers, claws, and teeth coexist with wings. These finds tell us that the leap from ground-dwelling dinosaur to flying bird wasn't a single heroic moment, but a gradual series of changes across countless generations. Now bring this abstract history a little closer. Think about the songs you hear outside your window. A mockingbird's mimicry, a blackbird's flute-like call, the mechanical trill of a wren. Those sounds are not just background ambiance. They are a living soundtrack of an ancient lineage. Call and response, territorial songs, mating displays. These behaviors evolved in the shadow of ancient pressures and opportunities. When a male bird sings at dawn, it's performing a behavior shaped by millions of years of natural history, carrying forward instincts that helped tiny dinosaurs survive when everything else was collapsing. The emotional pull is easy to miss until you reflect. When we watch a bird fly, we're watching resilience in motion. There's a humility in that, a reminder that massive forces can sweep away empires of species, yet lineages that adapt can persist in new forms. That continuity bridges deep time to the moment you see a feathered silhouette against the sky, or find a downy fluff caught in a branch. This makes birds more than biological curiosities. They're daily ambassadors from deep time. They invite us to think about survival, change, and the fragility of life. They also invite responsibility. The same adaptability that let birds survive the asteroid doesn't guarantee safety from modern threats. Habitat loss, climate change, and pollution are challenges they didn't face in the ancient past. So when the next robin builds a nest in your backyard, or a flock of geese crosses the sunset, there's a real, achievable way to honor that ancient lineage. Protect the spaces they need, reduce hazards where we can, and appreciate their presence. In practical terms, that can be simple. Leave a dead tree standing if it's not dangerous. It can host nesting cavities. Put up a bird bath, plant native shrubs, or reduce pesticide use. Small actions in your neighborhood add up to real habitat for smaller species that carry enormous histories. And when you see a bird, take a beat. Watch its feathers ruffle, listen to its call. Imagine the long lineage behind that moment. It's a direct line back to a world of scaly giants and volcanic skies, and it's unfolding in your own backyard. So the next time you glance up and see a pigeon coast on a thermal or a hummingbird hover with impossible precision, remember, you're witnessing the last living heirs of the Mesozoic. Their songs are echoes, their feathers are memories, and every flight is a continuation of a story that survived one of the most cataclysmic events in Earth's history. That's not just science, it's a reminder of survival, adaptation, and the subtle ways the past is woven into the present. We find their bones in deserts, cliffs, and quarries, in places where rock has been peeled back like the pages of a book. Imagine standing on a windswept badland, the sun flattening the world into ochre and bone white, and spotting a curved shard of fossilized rib half buried in the dirt. That little fragment is not just calcium turned to stone, it's a time capsule. It's a whisper from a vanished world, and sometimes, if you listen closely, it still has a story to tell. When I was a kid, I used to carry a pocket full of treasures home from every hike. A smooth river rock, a shell, once, to my parents' endless amusement, a small flake of something I swore was a dinosaur bone. Years later, standing in a museum under the hulking arc of a dinosaur's spine, I realized how right that feeling had been. There's a simple human urge in us to collect evidence that other lives existed, to bridge the distance between now and deep time. Fossils do exactly that. They are traces left when life met circumstance and got written into stone. Fossils come in many surprising forms. Sometimes it's a footprint pressed into mud that hardened and was buried, then polished by millions of years, until that resting step became a permanent impression in rock. I love the idea of a single footfall preserved, a moment of motion paused for eternity. You can almost imagine the animal pausing, weight shifting, a pause in breathing, and then the world sliding on and covering it. Other times, nature's preservation is almost cinematic, a feather locked in amber, trapped in resin, and carried through time as a tiny, perfect artifact. That feather might once have fluttered in an ancient forest, flicked a fly away, warmed a nestling. To hold that amber is to hold a sliver of a life forever still. Then there are nests frozen mid-moment, eggs arrayed in a crater like a paused heartbeat, or entire skeletons found articulated as if the animal died and was covered quickly, maybe by a sandstorm, a flood, a volcanic ashfall. Quarry workers uncover bones that lay beneath the surface for tens of millions of years. Cliffs reveal cross-sections of history like layered tape recordings. Each fossil is a message in a bottle from a past ecosystem. Some messages are long and complete. Others are brief, fragmentary. A tooth here, a vertebra there. But even fragments can rewrite our understanding of how life evolved, migrated, or behaved. What I find most moving is how these remains connect us across time. When paleontologists gently extract a fossil by the light of headlamps, they're doing more than collecting specimens. They're rescuing memories. They reconstruct bones into shapes we can recognize. They infer muscles and skin, gait and diet. And from those inferences, whole lives unfold in our imagination. Nothing truly disappears. Life leaves traces, in rock, in memory, in the shape of wings that still cut the air above us. That sparrow on your windowsill is the distant heir of a lineage that once left footprints in Cretaceous mud. There's something comforting and humbling about that continuity. The process that turns fragile organic tissue into stone is almost miraculous. It requires a precise set of circumstances: rapid burial, protection from scavengers and decay, mineral-rich water seeping in and gradually replacing organic material. Time, patient, indifferent, does the rest, compressing, mineralizing, rearranging. Radiometric clocks and stratigraphic layers help us date these finds, transforming them from romantic curiosities into calibrated data points on Earth's timeline. Even that technical language can't erase the poetry. The math tells us when, and the bones tell us who. And the human side of discovery is as interesting as the fossils themselves. Excavations are slow, meticulous work. You won't see it in the blockbuster movies. Crews of technicians hand-brushing dust, stabilizing fragments with consolidants, numbering each piece like a museum registrar. It's detective work mixed with craft, and every discovery is a collaboration across disciplines: geology, biology, chemistry, even art. Field notes, sketches, and photographs all form part of the record as a fossil transitions from buried object to exhibit to subject of scientific papers and public wonder. Maybe what makes fossils so powerful is that they teach us to think in two ways at once, about scale and about intimacy. We learn to span vast stretches of time, millions of years, and simultaneously focus on the minute details of a single tooth, a claw, a scale. That swing of perspective changes how we see our own place in the world. The same elements that made ancient organisms become fossils, burial, transformation, endurance, are metaphors for how we remember and are remembered. Our stories persist in other forms, in artifacts, in landscapes, in the species that carry traces forward. So when you next pass a cliff face, a quarry, or a sun-baked field, try to imagine the slow conversations the rocks are holding. Each fossil you see in a museum display or a sheltered dig site is a saved whisper, a bridge between then and now. Life may change, evolve, or vanish from a particular corner of the planet, but it rarely leaves no mark at all. The past isn't dead. It's folded into the present, like a page in a book we're still reading. Long before scientists had names like Tyrannosaurus or Triceratops, people found strange, enormous bones in the ground and told stories to explain them. Think about that for a moment. A massive femur sticking out of a riverbank, a heavy crescent-shaped tooth, a skull that looks like nothing alive anyone has seen. What would you do? For most people across history, the answer was to imagine. I remember the first time I stood at the base of a fossil mount in a museum as a kid. The bones were arranged into a posture so fierce it felt like the creature could take a step down off the platform and roar. My pulse quickened. I felt small in the best possible way. My mind filled in motion, sound, smell, details no bone could literally provide. That's exactly what our ancestors did and do. They give shape, motive, and story to the shapes they find. A giant femur could be the hind leg of a beast that raised villages. A huge jawbone becomes the proof of a monster slain by a hero. Across continents and centuries, communities named these remains dragon bones, giant men, or the remnants of the sky. In China, fossilized bones were literally sold as dragon bones and pulverized into medicines. In medieval Europe, odd bones fed tales of serpents and worms long before anyone thought of fossils as evidence of deep time. Those were not mistakes so much as the first human responses, narratives born of wonder and alarm. What's striking is how universal this instinct is. Societies unrelated by language or geography often developed dragon myths with striking similarities. Massive, often reptilian creatures that could fly or burrow, hoard treasure, or threaten communities. It's tempting to say we all saw the same thing in skeletons, but more interesting is the shared human habit. When faced with the unfamiliar, we use story to bridge the gap between absence and meaning. A jawbone doesn't come with a label. A story fills in the label. Science eventually gave names and frameworks where once there were only stories. Paleontologists dug methodically, compared anatomy, built trees of relationships, and placed these animals in deep, unimaginable stretches of time. That work is beautiful and necessary. It tells us how old these animals were, how they moved, what they ate, and how Earth itself shaped them. Yet science didn't eliminate the dragons. It redirected them. The raw awe didn't vanish. because we learned that a fossil belonged to a sauropod rather than a worm. If anything, the facts made the story richer. A creature that grew as tall as a 5-story building or one with teeth the size of bananas is still only slightly less miraculous when framed by a name and a date. This is personal for a lot of us. Maybe your grandmother told you a local legend about bones found behind the hill. Maybe your first dinosaur book showed a stegosaur lumbering across a sunset, and you carried that image into adulthood. Museums, films, toys, and bedtime stories are how these ancient animals live inside us. They become metaphors, power, extinction, survival, and they shape our fears and hopes. When we teach kids about extinction, we often reach for the dinosaur because it's both a concrete example and an emotional one. Something that walked, breathed, and then, irrevocably, stopped. That narrative power is part of the fossil's true inheritance. There's a tenderness to it, too. To imagine a dragon or a dinosaur is to refuse to let something vanish without memory. Naming, dramatizing again. This is how cultures honor the past. Scientists catalog fossils in journals and drawers. Storytellers keep them alive in songs, paintings, movies, and myths. Both acts are forms of remembering. Both turn cold, hard bone into a presence in our shared mind. So when you look at a fossil now, consider the two stories it carries. The scientific one mapped out by meticulous work, and the human one brimming with metaphor and myth. Neither cancels the other. Together they tell us why these creatures mattered then and why they matter now. Perhaps that's the truest legacy of dinosaurs. Not only their bones quietly telling of biological history, but the way those bones have been woven into human imagination. They lived once in flesh and blood, and they continue to live where it may matter most, in our stories. And so our journey drifts to a close. The giants are gone, but their echoes live on. In a gull's wing, a sparrow's song, bones underfoot. Tonight, picture a hush of Mesozoic woods. Feathers stir, a horned call rolls, footsteps fade. Sleep with the thought that giants still dream beneath the stars.